Hey everyone, and welcome. Today we are diving deep into a classic coding interview question that honestly is so much more than that. It's a powerhouse algorithmic pattern called subsequence validation. So let's get right into it and see how a really simple, elegant idea can solve a tricky problem with some seriously impressive speed.
So take a look at this. This one image pretty much captures the entire puzzle in a nutshell. It shows what we call the forward mapping and non-crossing rule. And trust me, this is the key to everything. The main idea? The connecting lines can stretch as much as they want, but they can never, ever cross. Keep that in your head. All right, so let's define the puzzle. What exactly is a subsequence? Well, imagine you're given two lists of numbers, or arrays. One is the main, big array, and the other is a smaller sequence. Our job, our mission, is to figure out if that smaller sequence is hiding inside the bigger one. And this is the important part, with its numbers in the exact same order.
And this slide, it lays out the one single rule you absolutely have to remember. On the left, we've got a valid subsequence. The sequence 1, 3, 4 is totally found inside 1, 2, 3, 4. All we did was skip over the number 2. That's perfectly legal. But on the right, that's a different story. Trying to find 4, 1 is a big no-no, because in the original array, the 4 comes after the 1. So here's the takeaway. Skipping elements is fine, but reordering them, absolutely forbidden.
Okay, before we jump into any fancy algorithms or code, let's think about how a human would solve this. Our own intuition is often the best starting point. And the best analogy I can think of is a simple shopping list. You've got the whole supermarket in front of you and your short list of things you need to find.
So what do? Our natural instinct is to just scan, right? We walk down the aisles. That's our big array, from start to finish. We're looking for the very first item on our list, which is a 1. We see a 5, nope, ignore it. Then we find the 1. Perfect. We mentally check it off our list, and then, what do? We start looking for the next item, which is a 6. We don't go backwards, we just keep moving forward. Simple.
And that right there brings us to the big question. Our human strategy is super simple. It's efficient. It just makes sense. So how in the world do we translate this really intuitive scanning method into a formal set of instructions a computer can understand?
Well, the answer is this incredibly elegant technique called the two-pointer method. It is the perfect way to turn our shopping list idea into a real algorithm. So let's see exactly how it works.
For this strategy, we've got two main characters in our story. First up, we have the iterator. You can think of this one as just relentlessly moving through the main array, one element at a time. It never stops, it never goes back. Then we have the tracker. Now this one is our checklist. It's patient, it only moves forward when the iterator finds the exact element it's currently looking for.
All right, let's trace this thing out. Our tracker starts at the very beginning of our sequence, and it's looking for the number 1. The iterator starts scanning the big array. First it sees a 5. Nope, not a match. It moves on. Next it sees a 1. Ding, 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 a match. The moment that happens, our tracker advances. It's now looking for its next target, the number 6.
And this right here, this is where the magic happens. The iterator just keeps on chugging along, right? It sees a 22, a 25. To us, this is all just noise. But look at the tracker. See? It hasn't moved an inch, it's not resetting, it's not getting confused. It is patiently waiting, holding its position, because the only thing it cares about in the entire universe right now is finding a 6. This separation of movement is the whole secret to the pattern. So after the iterator finds the 6, and then the -1, and finally the 10, we've done it. We've hit our success state. But how does the computer know it has succeeded? Well, the insight is actually pretty simple. If our tracker pointer has moved all the way to the end of the sequence array, meaning its index is now equal to the length of that array, well, that means we found every single item we were looking for, and we found them in the right order. Game over. We win.
And here's what all that logic looks like as actual code. It's surprisingly simple, isn't it? That let seqIdx equals 0 line, that's our tracking pointer. The for loop, that's our main iterator scanning through the array. And the most important line is right there in the middle. We only increment our seqIdx if we find a match. And that final return statement, it's just checking for that success condition we just talked about. That's it.
So, we know how it works. But now let's take a second to understand why. It's so perfect for this problem. Why is this approach not just a clever trick, but actually mathematically guaranteed to be correct and super fast? The proof is, believe it or not, beautiful in its simplicity. We only ever move through the main array in one direction, forward. We never ever go back. Because of that,
If we find our second target, we have an absolute guarantee that its position in the array comes after the position where we found our first target. That single-pass, forward-only motion is what naturally preserves the order for us. It's built right in.
And that simple logic also explains why it's so incredibly efficient. Its time complexity is O of n, which is really just a fancy way of saying we only have to make one single pass through the main array. The time it takes grows in a straight line with the size of the array, which is fantastic. And the space complexity, O of 1, or constant space. That means we barely use any extra memory, just one little variable to act as our tracker. No extra lists, no complex stuff, it's lean and mean.
So, you might be wondering, why not use other common tools? Like, what about a hash map? Well, a hash map is a bad fit because it's great at telling you if numbers exist, but it completely throws away their order, and order is everything here. And nested loops? Oh man, yeah, they'd work eventually, but they are wildly inefficient. You'd have to rescan the big array over and over again for every single number in your sequence. That's a performance nightmare.
Now here's the real payoff. By really getting this solution, you haven't just solved one little coding problem. You've actually mastered a fundamental pattern that can unlock the solutions to a whole bunch of other problems. This tracking pointer pattern is a total workhorse. You'll see it pop up in string matching problems, in algorithms for merging sorted arrays, and all sorts of other places. The key rule of thumb is right there on the screen. Whenever you find yourself needing to go through two different things, but one of them moves all the time and the other one only moves sometimes, that's your cue. That's when you should reach for the two-pointer technique.
And there it is. This is your interview pitch. If you ever get asked this question in a technical interview, this paragraph is your mic drop answer. It's confident, it's concise, and it shows you understand the strategy, the why behind it, and why it's so efficient. You're hitting all the key words: tracking pointer, order preservation, and optimal complexity.
So let's wrap it all up with a quick summary. The 4 big requirements of the problem. Order must be preserved. The numbers don't have to be next to each other. We have to find all of them, and we just need to return a simple true or false. And our 3 winning strategies to get there? The tracking pointer, preserving order with a single forward pass, and stopping early as soon as we found everything.
And that just about does it. You now have a seriously powerful new tool in your problem-solving toolkit. So I'll leave you with this final thought. Now that you've really mastered the tracking pointer, what other kinds of problems out there could you crack open with this same elegant pattern? Thanks for tuning in.